Welcome to Section 21.1, Part 1. This is the 207th session of the CISSP Exam Prep Series. In this session, we'll build a working picture of malware and viruses. We'll answer several questions. What exactly is malware, and why are its categories so blurry? Who writes malicious code today? What is a computer virus really doing? How do viruses spread from machine to machine? And what are the 4 classic propagation techniques? Why does this matter beyond the exam? Because containing malware is daily bread for a security team. Imagine you run defenses for a regional credit union. One infected laptop can seed a quiet outbreak across shared drives overnight. When you understand how these threats move and hide, you design controls that actually stop them. When you do not, you are only reacting after the damage lands. So, what exactly is malware? And why are its categories so blurry? Malware is any software built to carry an unwanted or harmful payload onto systems. It exploits weaknesses in networks, operating systems, applications, and even physical access. Some strains need a careless human to click or share before they spread. Others move on their own power across exposed machines. Here is the catch. Real specimens rarely sit neatly in one bucket. A single sample often behaves like a virus, a Trojan, and a bomb at once. So treat these labels as overlapping traits, not tidy compartments. Who actually writes malicious code today? The cast has shifted over the years. Early authors were highly skilled coders chasing bragging rights and, oddly, exposing real flaws along the way. Today, a script kiddie downloads a ready-made kit and fires it off with almost no understanding of how it works. Organized crime rings pick up those same tools for profit, harvesting banking credentials and identities at scale. At the top sit advanced persistent threats. Well-funded groups often tied to nation-states. These advanced persistent threat actors hoard zero-day exploits, flaws the vendor does not yet know about, so there is no patch and no easy defense. Their malware is precise, sometimes aimed at a single target, and very hard to shake. What is a computer virus really doing? Think of it like a biological virus with 2 jobs. First, propagation, the way it copies itself onto new hosts. Second, payload, the harmful action it was built to deliver. That payload might do something petty like flashing a rude message, or something ruinous like wiping a drive clean. Every virus is a small race against the defenders. The writer keeps inventing new ways to hide, and the antivirus world keeps catching up. Whatever the payload, it targets the confidentiality, integrity, or availability of your systems and data. How do viruses spread from machine to machine? Let's start with an overview, because there are 4 classic propagation techniques. The first attacks the boot process itself. The second infects executable program files. The third rides inside document macros. And the fourth injects itself into trusted system services. Each one answers the same question a different way. How do I reach a fresh victim without being noticed? Keep these 4 routes in mind as we walk through each. What is a boot record virus? It targets the tiny startup code that a computer reads first when it powers on. That code lives on a drive or removable media and tells the machine how to load the operating system. Because that startup area is only a few hundred bytes, it is far too small to hold a full virus. So the virus stashes its bulk elsewhere on the disk and leaves a pointer behind. When the system reads the infected startup record, it follows that pointer, loads the whole virus into memory, and may fire the payload. Picture a note on a locked door that says the real instructions are hidden under the 3rd floor mat. Boot defenses like a trusted platform module and secure boot help block this route. What is a file infector virus? This kind latches onto executable files and springs to life when you run them. On Windows machines, it favors program and script files, the ones that actually execute. It may quietly rewrite part of the program's code, or in some cases swap the whole file for a poison copy. A plain file infector is often caught by comparing a file's size, date, or hash before and after. One sneaky cousin is the companion virus. It creates a lookalike file with a name the system runs first, so typing a shortcut launches the fake instead of the real program. That is a solid reason to always run the full, exact file name you intend. What is a macro virus? Many everyday productivity apps let you automate chores with small embedded scripts. Those scripting languages are easy to write in, which is exactly why attackers love them. A macro virus hides inside a document and runs when you open the file. These spread fast in their heyday because the antivirus world simply had not braced for documents as a carrier. Think of a poisoned recipe card that cooks something nasty the moment you read it. The lasting fix was to stop untrusted macros from running without your explicit permission, which sharply cut their spread. What is a service injection virus? This technique hides by climbing inside processes the operating system already trusts. It injects its code into core running services, the ones your antivirus assumes are safe. By wearing that trusted disguise, the malicious code slips past scanners watching for obvious intruders. Imagine a con artist who steals a security guard's uniform to walk freely through the building. The strongest defense here is discipline patching, especially for browsers, media players, and helper tools that render web content. So let's bring it together. Malware is any harmful payload carrier, and its categories blur because real samples mix traits. Its authors range from bored coders to script kiddies, crime rings, and advanced persistent threats armed with 0 days. A virus lives to propagate and to deliver a payload against confidentiality, integrity, or availability. And it reaches new hosts through 4 classic routes: the boot record, file infection, macros, and service injection. Hold this map, and every countermeasure we cover next has a clear place. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 21.1, Part 2. This is the 208th session of the CISSP Exam Prep series. Having seen how viruses spread, we now look at how they hide, plus 2 more classic threats. In this session, we'll dig into evasion and 2 related code objects. We'll answer several questions. How do viruses fight back against scanners? What are the 4 evasion techniques you must know? What is a virus hoax? And why does it still cost you? And what is a logic bomb waiting for? Why does this matter beyond the exam? Because these are the threats that make detection genuinely hard. Picture yourself leading incident response at a logistics firm. Your scanner reports every system clean, yet performance keeps degrading and staff keep forwarding panicked warnings. Knowing how malware evades tools and how it hides in your own custom software is what lets you trust or distrust what your dashboard tells you. How do viruses fight back against scanners? As detection improves, virus writers engineer new tricks purely to survive it. This is an arms race, each side leapfrogging the other. So the 4 techniques we're about to cover all answer one question. How do I keep working after the defenders have seen my kind before? Keep that framing in mind, because each technique attacks the scanner from a different angle. What is a multipartite virus? It simply refuses to spread only one way. A multipartite virus mixes more than one propagation route in a single package. For instance, it might infect executable program files, which makes it a file infector, and also write itself into the boot record, which makes it a boot sector threat. The point is coverage. If your defense guard's only one doorway, the virus strolls in through the other. Think of a burglar who brings both a lockpick and a ladder, so a bolted door alone will not stop them. What is a stealth virus? This one lies to the operating system to cover its tracks. A stealth virus tampers with how the system reports its own files. When the scanner asks to inspect an infected area, the compromised operating system hands back a clean, virus-free copy instead of the truth. The scanner sees exactly what it expects and moves on, while the real infection loads quietly at boot. Picture a dishonest clerk who keeps 2 ledgers, showing auditors the tidy one while the real accounts stay hidden. What is a polymorphic virus? It changes its appearance every time it infects a new machine. The propagation and payload logic stay the same, but the outward signature shifts with each copy. The goal is to defeat signature matching, since a scanner looking for one fixed pattern never sees the same fingerprint twice. Vendors have cracked many of these techniques, but generating a reliable signature takes longer, so the virus roams free for more time. Imagine a con artist who wears a different face at every job while running the very same scam. What is an encrypted virus? It scrambles its own body with cryptography to stay unreadable on disk. Each infection uses a different key, so the main code looks completely different from one machine to the next. Only a small decryption routine sits in the clear, just enough to unlock and run the rest. The weakness is that this decryption stub tends to carry a recognizable pattern, and updated scanners learn to spot it. Think of a locked diary where the lock itself is a distinctive brand that gives away what it guards. What is a virus hoax, and why does it still cost you? Not every threat is real code. A hoax is a false alarm, a message warning of some unstoppable, uniquely destructive virus that no product can catch. There is no actual malware, yet the hoax still drains real resources. Well-meaning people forward it, flood help desk with questions, and sometimes delete healthy files on its bad advice. These warnings used to travel by email are now spread across messaging and social platforms just as easily. Treat the panic itself as the payload and verify before you forward. What is a logic bomb waiting for? A logic bomb is malicious code that hides quietly until a specific condition trips it. That trigger might be a date, a program launch, a particular login, or even a certain sequence of keystrokes. Many are planted inside custom software by developers who want their work to self-destruct if they are pushed out of the company. Others are woven deep into a live system, quietly sabotaging it so the author gets called back to fix the very problem they created. Picture a hidden switch wired into a building that only flips when one name badge stops scanning in. Because bombs often ride inside viruses and Trojans too, code review and separation of duties are your real defense. So let's bring it together. Once defenders catch on, viruses fight back with 4 evasion styles, multipartite spreads through several routes, stealth feeds the scanner a clean lie, polymorphic mutates its signature, and encrypted hides its body behind a fresh key each time. A hoax carries no code yet still wastes time, trust, and healthy files, so verify before forwarding. And a logic bomb sleeps until its trigger fires, which is why you review custom code and separate duties. Carry these forward, and the rest of the malware family will feel familiar. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 21.1, Part 3. This is the 209th session of the CISSP Exam Prep series. We finished the malware family by covering the threats that go beyond the classic virus. In this session, we'll round out the malware landscape. We'll answer several questions. What is a Trojan horse? And what disguises does it wear? How is a worm different? And what have famous worms taught us? What are spyware and adware after? How does ransomware turn encryption against you? And how do malicious scripts and zero-day flaws widen the attack surface? Why does this matter beyond the exam? Because these are the threats that most often reach your users directly. Imagine you defend a mid-sized law firm. A partner installs a free tool that looks helpful. A worm slips through an unpatched server, and a single click encrypts the case files. Recognizing each of these patterns lets you place the right control at the right layer before any of it happens. What is a Trojan horse? And what disguises does it wear? A Trojan looks helpful but hides a harmful payload inside. This is exactly why so many organizations forbid installing software the security team has not vetted. The disguises vary widely. Some Trojans pretend to be a game or utility while quietly hijacking your settings for ad revenue. Rogue antivirus fakes a security warning, then either steals your data or charges you to remove itself. A remote access Trojan opens a hidden backdoor that hands an attacker administrative control of your machine. And cryptomalware quietly steals your computing power to mine cryptocurrency for someone else's profit. The common thread is a friendly face wrapped around a hostile core. Where do Trojans lead once they take hold? Very often, straight into a botnet. When enough infected machines fall under one attacker, called a botmaster, they form a remote-controlled army. Picture a company whose network mysteriously crawls to a halt. Behind the scenes, dozens of its machines are quietly obeying an outsider, all hammering a single target website at once. That flood is a denial-of-service attack, and it can devour the organization's entire bandwidth. The fix is often simple: clean the infected hosts, and normal speed returns, but only if you knew to look. How is a worm different from a virus? A worm needs no human help at all. Where a virus waits for someone to click or share, a worm propagates on its own power across vulnerable systems. That self-driving spread is what makes worms so dangerous, because they can blanket the internet in hours. They carry the same destructive potential as other malware, but with the throttle wide open. Think of a fire that not only burns but lights its own next building, with nobody holding the match. What have famous worms taught us? 2 lessons stand out. The first is that patching speed is everything. One infamous worm tore through unpatched web servers, defaced their pages, and aimed a denial of service attack at a high-profile government site, even though a fix had been available for over a month beforehand. Prompt patching alone would have made it fizzle. The earliest major internet worm taught the second lesson, that attackers combine multiple weaknesses at once, exploiting mail flaws, weak passwords, a vulnerable utility, and trusted connections between systems in a single push. Defense in depth exists precisely because attackers rarely rely on just one door. Can a worm cause physical destruction? Yes, and one landmark case proved it. A highly sophisticated worm spread widely using several previously unknown flaws, shared drives, and infected removable media, yet it was hunting for one very specific type of industrial controller. When it found its target, it issued commands designed to physically wreck the equipment attached to that controller. If the reporting is accurate, this marked 2 firsts: a piece of code causing real physical damage to a facility, and malware used as a weapon between nations. It reframed malware from a nuisance into an instrument of warfare. What are spyware and adware after? Both interfere with how you use your machine, but for different ends. Spyware watches your activity and quietly reports it to a remote operator. It might wait for you to log into a bank, then ship your username and password straight to the attacker. Adware, by contrast, is chasing advertising money. Mild versions just push pop-ups, while nastier ones track your shopping and reroute you to competitors. Both fall under potentially unwanted programs. Software a user technically agreed to install that then does things they never wanted. Treat that fine print as a real risk, not a formality. How does ransomware turn encryption against you? Ransomware weaponizes cryptography, the very tool meant to protect you. After infecting a system the usual ways, it generates a key known only to the attacker and encrypts your critical files with it. Suddenly your own data is locked away, and a demand appears: pay by a deadline or lose access forever. Some attackers add a second threat: pay or we publish your sensitive data too. This puts victims in a brutal spot, and organizations with solid, tested backups fare far better because they can rebuild instead of pay. Be aware, too, that paying can be legally fraught, since some ransomware operators fall under economic sanctions that make payment itself unlawful. The lesson is blunt: backups and prevention beat negotiation. How do malicious scripts widen the attack surface? Automation cuts both ways. The same scripting languages that let admins provision accounts in seconds let attackers automate privilege escalation, backdoors, and command and control setup the moment they land on a host. The most slippery version is fireless malware, which never writes to disk at all. A user clicks a poisoned link. A browser flaw runs code that pulls the script entirely into memory, and the payload fires without ever touching storage. Tools that only watch for suspicious files on disk see nothing, which is exactly the point. Why are zero-day flaws so hard to stop? A zero-day is a flaw attackers have found, but the defenders have not yet fixed. 2 gaps keep you exposed. First is the window of vulnerability, the unavoidable delay between a threat appearing and a patch or signature being ready. Second is simple slowness, administrators who do not apply fixes promptly once they exist. Because you cannot patch what nobody has named yet, your real answer is defense in depth, many overlapping controls, so that when one misses, another still catches the attack. Think of it as several nets stacked at different heights rather than betting everything on one. So let's bring it together. A Trojan hides a hostile payload behind a helpful face, and it often drafts you into a botnet. A worm needs no human and spreads on its own, teaching us to patch fast, defend in depth, and respect that code can even cause physical harm. Spyware spies, adware cells, and both are unwanted programs you half agreed to. Ransomware encrypts your data for extortion, which is why tested backups matter so much. And scripts, fileless attacks, and 0 days remind us why overlapping controls beat any single defense. That completes the malware family. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 21.2. This is the 210th session of the CISSP Exam Prep series. In this session, we'll shift from threats to defenses. We'll answer several questions. Which platforms actually get targeted by malware? How does anti-malware software spot infections? How does integrity monitoring catch quiet tampering? And what do modern endpoint tools add on top? Why does this matter beyond the exam? Because choosing and tuning these controls is a core part of the job. Picture yourself standing up security for a growing design studio with a mix of desktops, laptops, and phones. Pick the wrong assumptions about who gets attacked, and you leave whole devices unguarded. Understand how each defensive layer works, and you build coverage that holds even when one layer misses. Which platforms actually get targeted by malware? For a long time, the answer was overwhelmingly one operating system, because it dominated the desktop and offered the biggest crowd to infect. That is still where most malware aims, but the gap has narrowed. Attackers have followed users onto other platforms, and threats against Mac and mobile devices have climbed sharply. The practical takeaway is simple. No operating system is a safe island. So every device in your fleet needs protection, not just the ones you assume are risky. How does anti-malware software spot infections? Its oldest and most common method is signature-based detection. The tool keeps a huge database of the telltale patterns of known threats and scans your storage against it. When it finds a match, it acts in one of three ways. If it can, it cleans and repairs the affected file. If it recognizes the threat but cannot repair it, it quarantines the file for a human to review. And if policy or the danger level demands, it simply deletes the file to preserve the system. The critical catch is that this defense is only as fresh as its definition file, so without frequent updates, it goes blind to anything new. What does anti-malware add beyond signatures? It adds heuristic, behavior-based detection. Instead of matching a known fingerprint, this approach watches how software actually behaves, flagging red flags like attempts to elevate privilege, hide their tracks, or alter unrelated system files. A common tactic is to quarantine a suspicious file and detonate it inside an isolated, monitored sandbox. If it misbehaves there, the tool blocks it everywhere and rapidly pushes out a new signature. This is why modern products catch far more than viruses, reaching worms, Trojans, rootkits, spyware, and more. And a tip worth remembering: if you suspect a fresh outbreak, contact your vendor directly rather than waiting on the next scheduled update. Centralized consoles let you enforce settings and watch alerts across the whole fleet from one place. How does integrity monitoring catch quiet tampering? File integrity monitoring gives you a second, complementary line of defense. It watches for unauthorized changes to files, which makes it great for spotting things like a defaced web page or an unexpectedly modified system executable. It works by storing a hash, a compact fingerprint, for each important file, then recomputing and comparing later. As long as a file is untouched, its hash stays identical. Change even a single byte and the hash shifts dramatically, raising a flag. So if a critical executable suddenly changes with no patch or install to explain it, that is a strong hint of infection. Think of it as a tamper evidence seal on every file you care about. What do modern endpoint tools add on top? They go well beyond classic antivirus, and there are a few names to know. Endpoint detection and response combines traditional protection with deeper analysis of memory, file system, and network activity, automatic isolation of suspicious behavior, live threat intelligence, and automated response. When a vendor runs all of that for you as a service, it is called managed detection and response, easing the load on lean security teams. A related tool, user and entity behavior analytics, builds a profile of each person's normal activity and flags deviations that may signal a compromised account. The key distinction is focus. Endpoint detection watches the device, while behavior analytics watches the user. Next-generation platforms increasingly bundle all of these into a single suite. So let's bring it together. No operating system is immune, so protect every device, not just the obvious ones. Signature detection matches known threats and lives or dies by fresh definitions, while heuristic detection watches behavior to catch the unknown. Integrity monitoring uses file hashes as tamper-evident seals against quiet changes. And modern suites layer on endpoint detection, managed services, and user behavior analytics, watching both the device and the person. Stack these thoughtfully, and a threat that slips one control still meets another. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 21.3. This is the 211th session of the CISSP Exam Prep series. In this session, we'll turn from malicious code to attacks on the applications themselves. We'll answer several questions. What is a buffer, overflow, and why does it keep happening? How does timing become a weapon? What makes backdoors so dangerous? How do attackers climb from user to administrator? And what new risks arrive when applications learn to think? Why does this matter beyond the exam? Because these flaws live in the software your organization writes and buys every day. Imagine you advise the development team at an online ticketing company. A single unchecked input field or a leftover shortcut can hand an attacker the keys to the server behind your checkout page. When you can name these attack patterns, you can push for the exact coding habits and patches that shut them down. What is a buffer overflow, and why does it keep happening? It happens when a program accepts input larger than the space set aside to hold it. That extra data spills past its reserved memory and corrupts whatever sits next door. In the worst case, the overflow overwrites executable instructions, letting an attacker run commands of their choosing on the server. The root cause is missing input validation, because many languages will not enforce size limits for you, and some developers skip the bounds checking to save time. Your job is to make sure input is checked for length, correct type, and sensible values before it is ever used. Picture pouring a gallon of water into a cup and letting the spill short out the outlet behind it. How does timing become a weapon? Computers do things in a predictable order, and attackers exploit the gap between two steps. The classic pattern is a time of check to time of use attack. First, the program verifies that a resource is fine to use, the time of check. A moment later, it actually uses that resource, the time of use. If an attacker can swap the resource in that sliver of time between the two, the program acts on something it never approved. Because the attacker is racing the legitimate process, these are also called race conditions, and more broadly, state attacks, since they exploit changes in system state. Think of a security guard checking your bag at the door, then someone quietly swapping the bag before you walk through. What makes backdoors so dangerous? A backdoor is an undocumented way into a system that skips the normal access checks. Developers sometimes add them during building and debugging to avoid logging in over and over, then forget to remove them or leave them deliberately to peek at data they should not see. Malicious code also plants its own backdoors to guarantee an attacker easy return access. The danger is precisely that nobody documented it, so it sits outside your controls, unseen and unmonitored. Anyone who knows the secret can walk straight in to steal data or watch users. Picture a builder who leaves an unmarked side door with no lock and never tells the owner. How do attackers climb from user to administrator? Once they gain any foothold, attackers usually want more power, and that leap is called a privilege escalation attack. A common tool is the rootkit, freely available online and built to exploit known operating system flaws. The attacker often starts with an ordinary user account grabbed through a stolen password or social engineering, then runs a rootkit to reach root or administrator level. From standard user to full control, that jump is the whole point. The good news is that one plain habit blocks most of these, keeping current with security patches, since consistent patching shuts the door on the very flaws rootkits rely on. What new risks arrive when applications learn to think? As software leans on artificial intelligence, whole new attack classes appear, and the machine learning security top 10 catalogues the worst of them. Attackers can hijack a model, bending its intended function toward tasks it was never meant to do. They can feed it subtly altered input, nudging a few pixels in an image to force a wrong prediction. They can poison the training data, slipping in malicious examples that corrupt what the model learns, and even plant hidden backdoors. They can invert a model to extract sensitive training data, or steal it outright by querying it enough to rebuild a copy. And they can strike the AI supply chain, compromising a pre-trained model or dataset before you ever integrate it. Your defenses are familiar in spirit, strict input validation, adversarial training, anomaly detection, watching for model drift, and fencing in what the model is allowed to learn in production. So let's bring it together. Buffer overflows spill oversized input into neighboring memory. So validate length, type, and value. Timing attacks exploit the gap between checking and using a resource, the race condition. Backdoors are undocumented entrances that bypass your controls entirely. Privilege escalation, often via rootkits, turns a small foothold into full administrative control, and steady patching blocks most of it. And AI-powered software adds fresh risks, from poisoned data to stolen models, defended by validation, monitoring, and tight boundaries. Name the pattern, and you can prescribe the fix. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 21.4. This is the 212th session of the CISSP Exam Prep series. In this session, we'll focus on injection, one of the most common ways attackers break into applications. We'll answer several questions. What is an injection attack at its core? How does SQL injection work? What happens when the attacker cannot see the results? What is code injection more broadly? And how does command injection reach the operating system itself? Why does this matter beyond the exam? Because injection flaws sit near the top of every serious list of web risks. Picture yourself reviewing a customer portal for a healthcare provider. A single search box that trusts user input can expose every patient record behind it. When you understand exactly how these attacks are shaped, you can spot the vulnerable code and demand the right protections before the portal ever goes live. What is an injection attack at its core? At heart, it is tricking an application into treating your input as instructions instead of data. The attacker supplies specially crafted input, and the application either executes it or passes it to a back-end system that does. We usually name the attack after whatever it targets or the payload it delivers. So you will hear of SQL injection, command injection, and many others. The common thread never changes. Untrusted input crossing the line into code. Think of slipping a forged order into a stack of paperwork and watching the clerk carry it out without question. How does SQL injection work? Many applications take your input and stitch it directly into a database query. Normally you search for a product, and the app builds a tidy query to fetch matching items. But if the app blindly glues your text into that query, you can add your own database commands to it. A crafted entry can close off the intended query and append a second one, say, to dump customer names and card numbers. Because commands can be chained, the same trick can also modify records, drop entire tables, or wreck availability. This is why input must never be trusted as part of a query. Picture handing a librarian a request slip that secretly also says, "And bring me everyone else's private files too." What happens when the attacker cannot see the results? Many vulnerable apps never show the query output, but that does not make them safe. Attackers turn to blind SQL injection, and the first flavor is content-based. Here the attacker injects a condition that is always true, then one that is always false, and simply watches how the page changes. A true condition returns the normal record, a false one returns nothing, and that difference alone confirms the flaw is real. It is slow and indirect, but it works. Imagine probing a locked room by asking yes or no questions and reading the guard's reactions. Is there a way to attack when even the page looks identical? Yes, through timing-based blind injection. When the content never changes enough to read, the attacker uses the clock instead. They inject a command that tells the database to pause for a set number of seconds before responding. If the page comes back instantly, the app is probably safe, but a deliberate delay reveals the vulnerability. Cleverer still, an attacker can extract secrets one character at a time by asking, "Does this letter match?" And if so, wait. Tools automate this until an entire password falls out. Think of knocking on a wall and timing the echo to map what is hidden behind it. What is code injection more broadly? SQL injection is just one member of a larger family called code injection, where attacker-written code slips into the developer's legitimate code. Any place that folds user input into executable instructions is a candidate. The same idea targets a directory service in an LDAP injection, an XML backend in an XML injection, or even tries to load a malicious dynamically linked library. A modern twist involves large language models, where a downstream system blindly trusts the model's output and passes it along unchecked. If an attacker poisons the prompt, the model can return a hostile payload that the next component dutifully runs. The lesson is universal: validate and escape input, and never blindly trust generated output either. How does command injection reach the operating system itself? This is an especially dangerous cousin, because the target is the server's own command line. Some applications reach back to the operating system to run a command, perhaps creating a folder for a new user. If the app drops your raw input straight into that command, you can smuggle in a second command of your own. On many systems, a simple separator character tells the shell, "And now run this too." An attacker can turn an innocent folder creation feature into an instruction that deletes entire directories. Picture a vending machine that takes your button press, then also executes whatever you scrawled on the coin slot. The defense, as always, is rigorous input validation before anything touches the shell. So let's bring it together. Injection means tricking an app into running your input as instructions. SQL injection folds hostile commands into database queries, exposing or destroying data. When results are invisible, blind attacks read the page's content or its response timing instead. Code injection generalizes the idea across directory services, XML, libraries, and even AI output. And command injection reaches all the way to the operating system shell. Every one of these bows to the same discipline: validate and escape untrusted input. Always. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 21.5. This is the 213th session of the CISSP Exam Prep series. In this session, we'll look at how attackers exceed the access they were granted. We'll answer several questions. Where do we go for trusted guidance on web risks? What is an insecure direct object reference? How does a directory traversal attack escape its boundaries? And how does file inclusion turn browsing into code execution? Why does this matter beyond the exam? Because authorization gaps let ordinary users see and do things reserved for others. Imagine you secure a document portal for a city government. If a resident can nudge a number in a link and read someone else's private filing, you have a breach without a single line of malware. Understanding these flaws lets you insist that every request is checked for permission, not just authenticated. Where do we go for trusted guidance on web risks? A great starting point is the Open Worldwide Application Security Project, a non-profit and community focused on securing web applications. It freely shares methodology, tools, and techniques for better coding and safer deployment. Two of its resources are especially handy: a running list of the most critical web application risks and a companion list of proactive controls to defend against them. Either one is a solid foundation for planning a security assessment or a penetration test. Think of it as a shared, community-maintained field guide to what actually goes wrong and how to prevent it. What is an insecure direct object reference? It happens when an application hands you data based purely on an identifier in your request, without checking whether you are allowed to have it. Say a link fetches a document by its number in the URL. There is nothing wrong with that by itself, as long as the app still verifies your permission. The trouble comes when it does not, because then you can simply change that number and pull up documents that were never yours to see. A real case involved a young person who noticed request records were numbered sequentially and read others' filings just by editing the identifier. The fix is straightforward. Check authorization on every object, every time. Picture a coat. Check that hands over any coat if you just say a different ticket number. How does a directory traversal attack escape its boundaries? Some servers are misconfigured so that users can wander the file system beyond the web content folder. The web content usually lives in one designated directory, and everything is assumed to sit under it. But on many systems, a special sequence in a path means go up one level. By stringing that sequence together, an attacker climbs out of the web folder and reaches sensitive files elsewhere, such as the file that stores hashed user passwords. If access controls do not stop them, the server happily displays that file in the browser, handing over a starting point for cracking credentials. Picture a hotel keycard that, through a flaw, also opens the door to the basement records room. How does file inclusion turn browsing into code execution? File inclusion takes traversal one dangerous step further. Instead of just reading a file and showing it to the attacker, it actually executes the code inside that file. There are two variants. Local file inclusion runs a file already sitting somewhere on the server, working much like traversal but with execution. Remote file inclusion is worse, letting the attacker run code hosted on a completely different server they control, without ever placing a file on yours. Once attackers succeed, they often drop a web shell, a small interface that lets them run commands and read results right in the browser. Cunningly, they may even patch the original hole behind them, both to avoid detection and to lock out rival attackers. Think of a burglar who not only gets in but installs their own remote control, then quietly fixes the broken window to hide the entry. So let's bring it together. Authorization attacks are about exceeding the access you were given, often with no malware at all. The Open Worldwide Application Security Project gives you trusted lists of the top risks and the controls that counter them. Insecure direct object references let you swap an identifier to reach others' data, so check permission on every object. Directory traversal climbs out of the web folder to grab sensitive files, so lock down file access. And file inclusion escalates browsing into remote code execution and web shells, so validate every path and input. In every case, authenticating a user is never enough. You must authorize each action. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 21.6. This is the 214th session of the CISSP Exam Prep series. In this session, we'll round out the web attacks by looking at how attackers abuse trust. We'll answer several questions. What is cross-site scripting? How do reflected and stored versions differ? How does request forgery hijack a user's or a server's trust? And how does session hijacking steal an active identity? Why does this matter beyond the exam? Because web applications are sprawling, public-facing, and full of trust relationships to abuse. Picture yourself protecting a community forum used by a national non-profit. One malicious post or one crafted link can quietly run code in every visitor's browser or move money on their behalf. Understanding these attacks lets you demand input validation, tokens, and session hygiene before attackers find the gaps. What is cross-site scripting? Cross-site scripting happens when an application lets an attacker inject their own web code into a page that others will view. The application trusts input and then renders it, so the attacker's script runs inside the victim's browser as if the site itself put it there. A harmless demo just pops up an alert box, but a real attack can capture passwords or hijack accounts. The whole class exploits the trust a user places in a legitimate website. Think of slipping a fake announcement onto a trusted community bulletin board, one that quietly picks the pocket of everyone who reads it. How do reflected and stored cross-site scripting differ? The difference is where the malicious script lives. In reflected cross-site scripting, the script rides along in the request itself, often hidden inside a crafted link. The victim clicks a link that looks like it points to a real, trusted site, and the site bounces that script straight back into the page and runs it. Stored, or persistent, cross-site scripting is nastier, because the attacker plants the script on the server itself, say in a forum, post, or comment. Now it fires for every future visitor automatically, with no special link required. There is also a sneaky variant that manipulates the page structure inside the browser, the document object model, without ever changing the server's code. The universal cure is input validation and output encoding, so user content is never treated as runnable script. How does request forgery hijack a user's or a server's trust? Request forgery tricks someone or something into sending a command it did not intend. The first form is cross-site request forgery. It exploits the fact that a user is often logged into many sites at once. An attacker embeds a hidden command that fires against a second site, and if the victim happens to be authenticated there, the command quietly succeeds, transferring money or changing settings on their behalf. The second form is server-side request forgery, where the attacker tricks the server itself into fetching a URL of the attacker's choosing, potentially exposing internal systems the public should never reach. Defenses include secret tokens the attacker cannot guess and checking that requests truly originated from your own site. Picture forging a signed note in someone else's name and handing it to a clerk who trusts the signature. How does session hijacking steal an active identity? Session hijacking is when an attacker seizes an already authenticated session and impersonates the legitimate user. There are a few common routes. They might capture the authentication details exchanged between client and server and replay them. They might trick the client into treating the attacker's system as the server, sitting in the middle before cutting the real user off. Or they might steal the cookie of someone who never properly logged out, or whose app manages cookies poorly. The results can be severe. So you defend with both administrative controls like anti-replay techniques and application controls like cookies that expire promptly. Think of someone slipping into a meeting under your still valid visitor badge the moment you step away. So let's bring it together. Cross-site scripting injects attacker code into pages, abusing a user's trust in a site. Reflected versions ride in a crafted link, stored versions live on the server for every visitor, and both yield to input validation and output encoding. Request forgery abuses trust in the other direction, tricking a user's browser or your own server into issuing unwanted commands, countered by secret tokens and origin checks. And session hijacking steals a live, authenticated identity, countered by anti-replay controls and expiring cookies. Across all of them, the theme is the same: never let trust go unverified. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 21.7. This is the 215th session of the CISSP exam prep series. In this session, we'll pivot from attacks to the controls that stop them. We'll answer several questions. How does input validation shut down bad input? What is a web application firewall for? How do you keep a database from betraying its data? How do you protect the code itself? And how do you build applications that bend without breaking? Why does this matter beyond the exam? Because these are the safeguards you will actually recommend and audit. Imagine you own application security for a fast-growing fintech. You cannot rewrite every line your developers ship, but you can insist on layered defenses that catch mistakes before attackers do. Knowing how each control works lets you build genuine defense in depth rather than a checklist that looks good but leaks. How does input validation shut down bad input? Input validation is your single most important application defense because so many attacks begin with untrusted input. The strongest form is allow listing, sometimes called whitelisting, where you define exactly what valid input looks like and reject everything else. If a field expects an age, you accept only a small integer in a sensible range. When the valid set is too varied to describe, you fall back to block listing, naming the dangerous patterns to reject instead, though it is easier to slip past. One rule is non-negotiable. Validation must run on the server, never only in the browser, because client-side checks are trivial to bypass. Picture a bouncer who admits only names on the guest list, rather than one who just turns away a few known troublemakers. Why do meta characters and parameter pollution complicate this? Some characters carry special programmatic power, like quotes, semicolons, and ampersands. And attackers exploit that power to break out of data and into code. The countermeasure is escaping, marking such a character as ordinary so it loses its special meaning. But attackers adapt, Parameter pollution sneaks past filters by sending two values for the same input, betting the platform validates one and executes the other. A firewall that inspects the first copy may wave through the malicious second copy. The lesson is humbling. No single filter is perfect, so you layer controls and keep platforms patched. Think of disarming a trap by taping over its trigger, only for someone to wire in a second hidden trigger. What is a web application firewall for? A web application firewall adds a protective layer in front of your web server. Unlike a network firewall, it works up at the application layer, inspecting the actual content headed to your app. It receives all incoming traffic, applies validation using allow lists or block lists, and blocks malicious requests before they ever reach the server. It does not replace secure coding, since applications still contain flaws when testing falls short or patches lag, but it catches a great deal on the way in. Picture a mailroom that opens and screens every package before it reaches anyone's desk. How do you keep a database from betraying its data? Two ideas matter here. First, defend the queries. Parameterize queries and stored procedures separate code from data. So user input is passed in as a defined value that can never be executed as a command, which neatly defeats injection. Second, defend the data itself. Data minimization is the strongest move. Simply do not collect or keep sensitive data you do not need, because you cannot lose what you never held. Tokenization swaps a real identifier for a random stand-in with a guarded lookup table to reverse it. And hashing replaces a sensitive value with an irreversible fingerprint, made even tougher by salting it with a random value to resist pre-computed cracking. Picture keeping customer secrets in a vault, but better yet, not keeping the ones you never needed at all. How do you protect the code itself? Developers must safeguard how code is created, stored, and delivered. Code signing lets a developer digitally sign their software so users can verify it is authentic and unaltered, though be warned, signing proves origin, not safety, since signed code can still be malicious. Code reuse through third-party libraries and software development kits saves enormous effort, but every borrowed dependency inherits someone else's flaws, so you must track and patch them. Software diversity means avoiding a single point of failure in your source, executables, or compiler. Code repositories centralize source with version control, logging every change and enabling rollback, which supports both collaboration and auditing. And integrity measurement uses hashes to confirm that what reaches production exactly matches what was approved, flagging any tampering. Think of a supply chain where every part is signed, sourced from vetted suppliers, logged, and checked against the blueprint before assembly. How do you build applications that bend without breaking? Resilient design relies on two related properties. Scalability means an application can take on more resources as demand grows, either by beefing up an existing instance, called scaling up, or by adding more instances to a pool, called scaling out. Elasticity goes further and does this automatically, provisioning resources when load rises and releasing them when it falls, which controls both performance and cost. These traits are hallmarks of cloud platforms and a major reason organizations adopt them. Picture a bridge that can add lanes during rush hour and quietly retire them when traffic thins. So let's bring it together. Input validation, done server-side with allow lists, is your frontline defense, reinforced by escaping and layered against tricks like parameter pollution. A web application firewall screens traffic at the application layer before it reaches your server. Databases are protected by parameterized queries and by minimizing, tokenizing, and hashing the data they hold. Code is safeguarded through signing, dependency management, diversity, repositories, and integrity checks. And resilient applications scale and flex with demand. Layer these controls, and a single mistake no longer means a breach. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 21.8. This is the 216th session of the CISSP Exam Prep series. In this session, we'll close the loop with the secure coding habits that prevent the flaws we've studied. We'll answer several questions, Why can source code comments become a liability? How does good error handling protect an application? What is wrong with hard-coded credentials? What risks come with AI-assisted coding? And how does poor memory management undermine security? Why does this matter beyond the exam? Because the same handful of coding mistakes keep resurfacing no matter the language or framework. Picture yourself mentoring developers at a rapidly scaling startup. The frameworks change, the team grows, but sloppy comments, weak error handling, and leaked credentials show up again and again. Instilling these habits is how you stop tomorrow's breach at the keyboard, long before it reaches production. Why can source code comments become a liability? Comments are genuinely valuable, documenting design choices and helping the next developer understand the code. The problem is when they end up in the wrong hands. A comment can hand an attacker a roadmap of how the code works, and sometimes it even contains secrets that should never be exposed. For compiled programs, this is less of a worry, since the compiler strips comments out automatically. But web applications can expose their source directly, letting outsiders read every note left behind. The rule is simple. Keep comments in your archive source for future developers, but remove them from anything published to the internet. Picture leaving detailed renovation blueprints taped to the front door of the building. How does good error handling protect an application? Attackers deliberately push code into strange situations to see how it breaks, so your code must expect the unexpected. It is not enough to confirm that a field holds an integer, because someone might paste a 50,000-digit number to trigger an overflow. Many languages offer try and catch structures, where risky code sits in a try block and the catch block defines exactly how to respond when it fails. Crucially, error handling is a second layer behind input validation, catching anything your validation missed, which is defense in depth in action. But there is a flip side. Overly detailed error messages can leak the inner workings of your code and invite attack. The guideline is to show users only the minimum they need, while logging the full details privately for your developers. Think of a receptionist who politely says there was a problem, while the full incident report goes quietly to the back office. What is wrong with hard-coded credentials? Baking usernames and passwords directly into source code is a persistent and dangerous mistake, and it comes in two flavors. The first is a hidden maintenance account, a backdoor the developer adds to regain access if authentication fails. If that backdoor password ever leaks, every deployed copy of the code is compromised at once. The second is embedding credentials for other services right in the code. So if the code is disclosed, those secrets go with it. This happens all too often when developers accidentally push code-holding keys or passwords into a public repository. The fix is to keep secrets out of source entirely, using secure configuration and secret management instead. Picture writing the master keys combination directly on the lock for anyone to read. What risks come with AI-assisted coding? As developers lean on artificial intelligence to write code faster, new hazards appear. These tools can hallucinate, confidently suggesting libraries, functions, or interfaces that do not actually exist or behave nothing like expected. Worse, because they learn from vast amounts of public code, they can quietly recommend insecure snippets carrying known vulnerabilities, outdated functions, or subtle logic errors. Speed is seductive, but blind trust is dangerous. The discipline is unchanged from any other borrowed code. Critically review, independently verify, and thoroughly test everything the AI produces before it ships. Think of a fast but unproven intern whose work you always check before it reaches a customer. How does poor memory management undermine security? When applications manage their own memory, careless handling can cripple the whole system, and two problems stand out. The first is resource exhaustion, where a system consumes all its memory, storage, or processing until it grinds to a halt. A classic cause is a memory leak, where an application keeps requesting memory and forgets to return what it no longer needs, slowly starving the machine until it crashes. The second is pointer dereferencing gone wrong. A pointer holds the address of data elsewhere in memory, and following it is normal. But if the pointer is empty, a null value, dereferencing it triggers a null pointer exception. At best, the program crashes and hands an attacker useful debugging clues, and at worst, it lets them bypass security controls entirely. Security professionals should partner with developers to catch these issues early. Picture a warehouse that keeps taking in stock but never ships any out. until the aisles are so jammed nothing can move. So let's bring it together, and with it, our entire journey through the CISSP domains. Comments help developers, but must never leak to the public. Error handling anticipates the unexpected and hides its inner workings while logging the details. Hard-coded credentials, whether backdoors or embedded secrets, must stay out of source code entirely. AI-assisted coding demands the same critical review as any borrowed code. And sound memory management prevents exhaustion and null pointer failures. Secure coding is where every principle in this series finally meets the keyboard. Carry these habits forward, and you carry the whole discipline with you. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I wish you all the very best with your CISSP examination preparation.